In this video, we want to talk about this NeurIPS 2022 paper called When Are Graph Neural Networks Better Than Structure-Agnostic Methods? In many cases, there are meaningful relationships between the different items and examples in your dataset that can be utilized in order to lead to a more efficient predictions being made on them. For example, if you have like a social media graph, the representations, whatever representation you could think of, between the people who, let's say, follow each other or have something in common, probably is more informative than those two people who have nothing to do with each other. So this type of things would call for some types of graph-based structuring of the data and utilizing these types of relationships via the definitions of different types of edges, which led to the development and introduction of graph neural networks. I actually have a series of videos on graph neural networks, which is linked in the descriptions if you want to get more familiar with the theoretical backgrounds required for understanding what graph neural networks are, why they were introduced, and what they do. Nonetheless, assuming that you are familiar with graph neural networks and its operation, you know that its main novelty is in utilizing the structure between the different features, different nodes, in order to make predictions. Now, in summary, this specific paper is going to focus on what types of characteristics that have to do with certain assumptions that are made regarding graph neural networks are pivotal in trying to understand and intuit when these types of architectures are useful and beneficial in improving the efficacy of predictions, and when they are actually not a suitable architecture to be used. Namely, they focus on decoupling the impacts of the informativeness of the feature vectors associated with individual nodes by, for example, changing the signal-to-noise ratio and things like that, and the structural assumptions such as the density of edges in the network and the assumption of homophily, which it has to do with whether or not, if two nodes are connected, whether or not the representations are expected to be more similar, more different, in the case of the actually opposite of homophily, or whether or not it's completely irrelevant, or just, let's say, we have random structures. So this paper is going to observe those things, and it's mostly going to agree with a lot of assumptions that are intuitively have been made on graph neural networks, and it's a very interesting article. It has been written by AI Lab VUB and IMEC in Belgium. Right, let's get into the paper. Now, graph neural networks are commonly applied to graph data, of course. Its performance is poorly understood, so which is the main motivation for this article. They're going to focus on trying to understand the effectiveness of graph representations and when it's actually good. In this work, they're going to focus on a shallow GNN with two layers for input graphs with different structural properties. That this different is important, so they have different structural properties in one domain and feature information in another domain, and then they try to decouple the impact of these two in order to better understand what the hell is going on. And the results indicate that GNN implicit architectural assumptions are tightly related to the structural properties of the input graph and may impair its learning ability, which is something that was expected. Now, going inside the introduction of this article, again, the motivation for this article is that the GNN performance is often poorly understood, and what kind of characteristics in the data and model and things like that have to do with whether or not the GNNs are going to be effective, which comprises the main motivation for this article. What they focus on analyzing is the underlying assumptions of the GNN architectures, and they show that they are key in determining the expected performance. Again, the main idea of graph neural networks is that relational information, for example, connections, can provide additional information to solve the target task more efficiently. Again, the famous example of friendship links in a social network, which has to do with the prediction of a person's interest. They show that due to fundamental limitations, which again has to do with the oversmoothing, which has to do with the architectural capacity of the GNNs, basic GNNs are unable to learn useful representations when certain assumptions that have to do with the GNNs are not met basically by the data domain. They also provide evidence that more advanced GNN architectures, such as film, can avoid this limitation. But again, they may still fail to exploit structural information altogether to reduce basically themselves to feature-only methods or just to ignore the relationship. So again, it boils down to the fact that in order for the GNN to work, the structural information has to be informative. It has to be something other than random. And they also remark on the fact that the more advanced version of GNNs can compensate for that, but basically kind of reducing the reliance on that structural information and sort of letting it go in order to perform as good as, let's say, a normal MLP that does not utilize that relational information would do. The main contributions are the proposition of an empirical because they run experiments and they have like augmentations to work on a real world data set and modify like the different aspects of features in the structures, model agnostic method for decoupling feature and structure and information. So again, it has to do with either augmentations or graph generation, and by these two they can modify the things that are intuitively expected to have an impact on the outcome. And second, the disclosure of new empirical insights on how GNN performance can be hindered by input graphs' structural properties. So the way that they work with the feature is that they work with the feature signal to noise ratio SNR, and for the structures they work with edge density and homophily. And they basically work with the message passing graph models such as GCN and try to understand what these have to do with the implicit assumptions of these types of message passing models. We have different sets of operations for each original graph. These operations are set in the product, destroy structure, and as well. The first part is about artificial graph generation, which they follow the stochastic block model or SBM. They are able to use that in order to kind of change the edge density, homophily, and the feature SNR. They generate graphs with 1,000 nodes, and each node is going to be assigned a label to a class-balanced binary node classification problem. Therefore, it's going to have like 500 nodes of each class. All artificially generated graphs that they had in this paper are available for repeatability. Next, the real-world benchmarks that they have. So there are two types of node classification problems, mainly in the real world. One of them is the homophilic assumption, such as citing networks of Cora and CiteSeo. So if a paper is citing another one, their conceptual ideas are probably similar, their topics are similar. But there is also the heterophilic graphs, in which if you take two nodes that are connected, the presence of edge between them is going to indicate that their representations actually have to be more distant from each other. So again, structural information is important. Nonetheless, it has a certain property that is actually in opposition to the general assumption of, let's say, graph neural networks that has to do with adding the representation of the neighboring nodes in order to kind of augment or improve the representation of the centering node. And it's not trivial whether or not it's a beneficial thing to have that type of heterophilic structure being utilized in a graph neural network. As for the graph mutations, they work on random connectivity, namely shuffling the columns of graph connectivity matrix, and there's also a random feature assignment which randomizes the attribution of feature vectors across all the nodes. Again, these are the graph mutations that they have in order to kind of apply on the data sets. As for the model, they focused on graph convolutional networks. In addition, they have had like advanced models such as APPNP and film as well. As for the implementation, they use the PyG library or torch geometric library, and all the representations are been using GraphGym framework. Now let's talk about the results. Does structure encoding always contribute to learning useful node representations? The first question that they strive to answer. One thing they show is that graph convolutional networks is not seen to be able to fully leverage them when the structure input graph was meaningless towards its inherent assumptions, leading to this significant loss of performance even relative to its structure-agnostic character. So if you have an MLP, and if you have a normal graph, and if the normal graph utilizing the structure in the graph neural network, if the structure is nonsense, then it's going to be more difficult for a model like GCN, which is equipped with the inclination towards utilizing the structure to compensate for its meaninglessness in order to lead to, let's say, kind of remove that type of information which is inclined to learn based on its architectural design, compared to just like applying MLP on individual nodes and getting the output. The GCN models need both feature and structural information, of course, to be meaningful in order to learn useful node representations. Otherwise, it's not going to be good. As for the homophily, there is this part. So it mentions that the inspection of GCN's response to different homophily conditions reveals its adequate performance on the most, meaning the most homophilic like the Cora, and least homophilic like the Texas or the other one, original graphs. Meaning that if the structure has information, whether that information indicates the similarity of the representations of the nodes that are connected, or if it's remarking upon the dissimilarity of those, in both two cases the GCN has resulted in informative representations. Nonetheless, in the cases that it was not meaningful, meaning that, let's say, random structure, or whether, let's put it this way, when the presence of connection between two nodes did not say much about what their semantic representations are, or let me put it this way, how they are positioned with respect to each other, then in those cases the GCN is going to be very limited. At the same time, and yeah, what you can see here is that if you have informative features and informative structure, GCN is going to be better than MLP. Now, if you turn the structure to be uninformative, immediately the GCN is going to drop to 69, and you can see that MLPs is still going to remain high, but the GCN is going to be 69 now. In case of the uninformative features, but informative structure, again, GCN is better, even though the overall performance has dropped. But in the case of uninformative, both they are kind of similar, but GCN is worse. So all in all, in order for a graph neural network connection architecture to work, you have to both have informative features and informative structure. Informative features in order to just orally get a good performance metric, and informative structure in order for you to utilize the capabilities of the GCN, which has to do with aggregating the neighboring representations in order to improve the semantic interpretability of the representation of each node. Consistency. So again, this is if the structure is meaningful, kind of regardless of what its meaning is, it's still doing like non-meaningful structure in terms of utilizing the capabilities of the GCN, and how they measured it is using empirical experiments. What this remarks upon is drawing attention to potential insufficiency of solely resorting to homophily-related assumptions to steer GNN architecture research endeavors. They also observe and verify a significant loss of performance when you kind of deal with when structure and or feature information of the original graph are destroyed, as shown in the table before, except for when homophily is close to 0.5. Mediocre performance on the original graph on par with the random structure mutation. They kind of conclude that being as connected to other nodes of a different class as to those of the same class, in other words, when the edges are not informative, it's going to lead to an uninformative structure. Therefore, based on which this GCN will perform local smoothing operations that will decrease the feature expressivity and would lead to a bad poor node representations and therefore poor performance. As for the edge density, they want to kind of understand that again. When structural information is meaningless, the most sparsely connected structure leads to the best result is one thing that they find. And if structural information is irrelevant, we should expect better node representation from structures with fewer connections. As for the feature SNR, the results indicate a significant loss of performance for the random connectivity mutation in comparison with the original version, even in the scenarios when the base features are easily separable by a feature-only method. Now let's go to the tables here. First, we have look here, for example. You have a multi-layer perceptron baseline for original features. And you also have the MLP for the random feature assignment. Let's consider the original feature first. You can see that, let's say the structure is the original, you have 0.78. With this version of homophily, again, 71 is kind of the MLP baseline if you ignore the architecture altogether. So if you consider the architecture by using the GCN, with the homophily of 0.2, which is low homophily, you're going to do better. With high homophily, you're going to do better, but with mediocre homophily, which in other words means that the structure did not have information, you're going to do actually worse. Which is because in this case, the structural edges do not have information, because based on those, you cannot conclude whether or not the representations have to be similar or different. As for the density, you can see that when you have like random structures, the smaller density or sparser network is going to lead to better results here. When you go to the random feature assignment, you have 0.49 as the MLP. You can see that you have this kind of like structure. So if you keep the structure as the original structure, there are like some inconclusive results based on the, and it appears that, so for example, if you go to the structure original and random, and based on the density, you have the random feature assignment, you can see that you increase the connectivity, the result is going to do better, and you decrease it, it's going to, so it's not as clear as the case of the original features, but there seem to be some patterns there. As for the table 3, which is the node classification performance of GCN and MLP, SNR, so you have the MLP baseline with different versions of SNR. So for example, let's take this one. Let's say SNR is 2.0, MLP is doing perfect. Now if the structure is original, GCN is going to do perfect as well. If it's randomized, it's going to go down. And likewise for the 1.5 SNR, let's go back to very small SNR of 1.0. You have 0.51%, sorry, 51% MLP baseline, which is what you get with the random information, but with the original, you actually are going to be able to do better. So with this kind of low SNR, the structure is important. Then you go to the 71%, 1.2, again, the structure is important. 91, less important. With this high level of SNR, as you can see, that information, representations are clearly statistically sufficient for that, and therefore it doesn't really make much sense to even use those structural information, given that, let's say, what you want in the target task is already there. Another question that they talk about is, can advanced GNN architectures cope with poor feature or structural information? So by advanced architectures, meaning like going beyond the normal graphical convolutional networks, like they work with RevGCN and film. So let's read this part. The trend in homophilic graphs informative Cora cites here supports that all models perform adequately on the original graph versions. In these versions, RevGCN and film are, however, associated with lower performance. Contrastively, these are the models that can better cope with the structural information loss, being the only ones that can reach the performance of the feature-only model, the MLP, in the random connectivity scenario. So these models are more robust. Nonetheless, film is going to exhibit feature-only level performance for the original Texas graph, while all other models appear to be hindered by such a structure to the point of losing base feature expressiveness. They conclude that for some models, random connectivity seems to be easier to handle than the original graph structures of Chameleon and Texas, meaning that for some graph models, if you have random connections, actually it's going to be leading to better results than utilizing the actual connections that are given. Again, all of these indicate that, let's read this part again, it's as important. There are several levels of structural impact on GNN performance. There are structures that help, structures that hinder, and structures that are ultimately irrelevant for the classification outcome. Let's go back to this table, which is table 4. Consider the random feature assignment. In the case of random feature assignment, meaning let's call it uninformative features, if you consider the Texas data set, if you have the original structure versus random structure, let's read this informative and non-informative structure. The case of informative structure, the GCN is doing 49, the non-structure is going 51. So this is for the case of GCN. Whereas film is doing 0.57, and again, the baseline for MLP is 54. You go to the case of informative features, GCN is going to do 53 and 49 in case of informative structure, non-informative structure. Again, Texas is a data set with less homophily. It's actually a heterophilic graph. Note that in this case, film is actually doing better than the MLP in the case of informative structure, and in this case as well. You have also this row, 96, 96, 69, 92, 92, which is GSN. GCN seems to be more sensitive to the basically the informativeness of the structure that the data has come with. As for the limitations of this work, let's read this part. They mentioned that the results that they had suggest that we should not only explore feature structure codependence, but also how models respond to certain combinations of graph properties, because we saw that the impacts on the different types of model outcomes was not very uniform. Let's say this model is less sensitive, more sensitive, things like that. This was not explored in this paper. Again, their method for losing structural information through random connectivity does not destroy all structural properties. And again, this transformation does destroy the original encoding of real intelligible links for the real-world benchmarks. So what they mention here is that the fact that they've worked with artificial graphs or a big part of this study might not reflect super well in the real-world data. And another thing is that they did not perform hyperparameter tuning, which could be important. And this concludes our discussion of this paper. Thank you for watching this video.